So where I left you with is this question on the aluminum magnesium phase diagram, which I'm going to bring up again. And I hope you had some time to think about it. Because, you know, thermodynamics is a bit like learning a language. It's fairly easy to get it passively to understand it. It's a bit harder to do it actively. So I asked you to think about how you would deal with this construction, where if you sort of look at it, the big picture, right? If you go down in temperature, at some point the liquid has to disappear, right? Because it's gone at the low temperature, and this new phase has to appear. And how can you make all the constructions to make that happen? So I've drawn in the notes and on the slides a few. The most likely one, or the most easy one, I would say, to draw, we really don't know what's likely unless we know more about the system, is that you have a combined eutectic and peritectic, right? So the liquid disappears through a eutectic, and then the new compound appears through a peritectic, and they're just somewhat separated in temperature, right? So this would be probably the most reasonable construction to make this thing happen. But you can get creative, right? So you could do, for example, well, what if you found out through some experiments that the compound appeared congruently through the melt, which is this case? So you would, how would you do this, right? You would basically draw the congruent point, and then that means you have to make the liquid disappear on both sides of that, on both sides of the composition. So you do just two eutectics, right? And you got rid of the liquid. You can make it more complicated by doing peritectics. So if I were to tell you that the liquid appeared peritectically, and how would people know this, right? First of all, if these temperature ranges are very narrow, it might be hard to see that, but people often see that from the microstructure that formed. If you remember what I told you, what has to happen in a peritectic is that the liquid has to attack one of the solids. In this case, right, the liquid has to attack the aluminum solid to actually make this phase. And if you had a lot of remnant of aluminum in the microstructure, you might actually see that it's a peritectic. So in this case, we've done, you know, a peritectic construction to make this phase appear. And then we still have to deal with the liquid disappearing. We've just done that through a eutectic. And now the eutectic is between the new phase and the other one. You can do a different peritectic, right? You can, here we did a peritectic with liquid and aluminum. You could do a peritectic with the liquid and this other compound. And that's what's shown here, right? Here you have a peritectic, the liquid attacks this compound, forms the new phase. And again, at some point, the liquid has to disappear, and now that happens in this eutectic. That's pretty much all the constructions I could come up with. I don't know if any of you tried and came up with more a different possibility. You're welcome to tell me, or if you don't want to do it now, send it to me if you want to have me check whether it's correct. But I came up with 4. I don't think there's a proof that there's only 4, but I mean, unless you do weird re-entrant behavior stuff, right? Okay. So what you should remember is, from class last time is that, actually let me leave this on sharing since I have to go back to slides soon, is that most of phase diagrams are made up out of these 3-phase constructions, right? Because you have to make phases appear and disappear, and you do that through eutectic and peritectic reactions. So that's pretty much all we're going to do about sort of construction of phase diagrams. The few remaining things I have to do is I want to give you a bit of insight in how to use phase diagrams, largely through examples in technology, how they're being used to sort of explain certain behavior. And then I want to spend a bit of time in showing you how you can even use phase diagrams to explain non-equilibrium behavior. You know, we think of phase diagrams as equilibrium behavior, and that's true. But if you're intelligent about it, you can actually sort of extrapolate a lot of non-equilibrium behavior from them. And I want to give you a few examples of that. And then at the end, I'll just show you a little bit how certain physics of entropy and energy shows up in phase diagrams, and I think by then will be done. So I want to start with an application out of metal hardening, and what I want to show you is a piece of data that, let's say you were given just this data. This is the thermal processing of an aluminum copper alloy. It's about 4.4 weight% of copper, so it's mostly aluminum. And this is aluminum copper alloys are the basis of what I would say the staple of the aerospace industry alloys. You know, if you go to your average airplane, it has an awful lot of aluminum, copper, and then some with other alloying additions in it. But they are usually first treated at high temperature. They're what's called solution treated. So you bring them to high temperature to bring all the elements in solution, and then they are annealed at low temperature. And in this case, I think this was 200 Celsius. Let me take my notes. Yeah. So this was done, yeah, here it says 204 Celsius. And what is shown here is the yield strength, and I like the right axis in MPa, but if you like PSI, there you go. The yield strength as a function of annealing time. And first of all, you know, it's important to sort of understand the values a bit, right? So the maximum yield strength is about 400 megapascal that you can achieve. To put that in perspective, right? So a typical low strength steel yield strength is about 200 megapascal. A super high strength steel is probably 1,000 megapascal order of magnitude. But since it's mostly an aluminum alloy, does anybody know what the yield strength is of pure aluminum? Like highly pure aluminum? It's only about 30 megapascal. So if you take pure aluminum, it's 30 megapascals. So it's actually a remarkably soft metal. So simply by a small addition of copper and the right heat treatment, you can actually increase that by more than a factor of 10. So those of you, of course, who have a material science background probably have an idea of what's going on, right? If you look at the phase diagram, let's go to the phase diagram. And I like this beauty because if you look at this phase diagram, this looks like, God, remarkably complicated, right? Look at that. It's like a mess of Greek letters. But the good news for us is that we're on this side, right? We're aluminum rich. So really, you could just kind of erase this stuff, right? Nobody cares because remember, phase diagrams are local. So we're working in this space here somewhere. Like 4 weight% is somewhere here, right? So we really don't care about all that other stuff. So what happens, so when you solution treat aluminum copper, so you bring it to high temperature, this is the single phase region here, you bring it to high temperature so it goes all in solution. And then when you cool it down and you anneal it at 200, 200 isn't even on here, but let's just take 300, right? You're now in a two-phase region. So you're in a two-phase region where you now will make an aluminum matrix with some second phase theta, right? And theta is an ordered compound. If you actually look at the atomic percentage, you see it's about 33, right? So it's actually Al2Cu. And so what happens here? Can somebody explain this behavior? Why does it do this and then that? Why does it do that? Classic exam question from Professor Ritchie in your prelim.
Do you have
precipitates? Okay, somebody was going to say something. Go ahead.
Do you have precipitates growing to a good, like the ideal size, like an hour, and then getting too big?
Yeah, so what happens here is a classic case of precipitation hardening, right? So you start with the matrix, it's solid solution to start with because it's quenched down. And then you start nucleating very small precipitates of the second phase. Actually, in the beginning, they're coherent with the matrix. That's what makes these alloys so special. And at that point, you have a lot of obstacles for dislocation glide, right? So the precipitation hardening, the precipitates make obstacles for dislocations, and that's what hardens the alloy. And what happens when you anneal for too long? because the precipitates want to reduce interfacial energy, you get more of them. You get the same volume fraction, but they are organized, you know, they become larger, so you get less of them. And since you get less of them, you get less obstacles to dislocation growth. And so now the yield strength actually goes down again. So this is something you can sort of look at, you know, and roughly estimate from a phase diagram why this might be the case. You know, you can read phase diagrams for iron carbon, so steel, in the same way to try to understand how they are hardened and how they are solution treated. Of course, it doesn't tell you, the thermodynamics doesn't tell you sort of about the time scale, of course, over which this happens, right? So in the 1990s, the aerospace industry thought they wanted to make planes even lighter, and you know, they were going to try to go to even lighter elements. And you know, we've talked about aluminum, right? Aluminum is already a very good compromise because its strength to weight ratio, when strengthened with alloying additions, is very good, and its price is reasonable, because otherwise we would make airplanes out of titanium, right? It's just not quite cost effective, and there are other issues with titanium, like problems with welding. But so for a long time, the aerospace industry thought if we could replace some aluminum and mainly also copper by lithium, lithium is the lightest solid element, right? Then we could do the same thing, and we'd have even lighter alloys. And the beauty is that aluminum lithium has a similar phase diagram. Here's aluminum, and you can bring lithium in solid solution. There's a phase you could precipitate out. And actually, in reality, there's a metastable phase here, which you can precipitate out, and it sort of acts almost like a stable phase. And so people made lithium aluminum alloys for the longest time, and Alcoa, which at that time was the Aluminum Company of America, Aluminum Company America, right? Which is in Pennsylvania, or was in Pennsylvania, invested all kinds of infrastructure, and it worked, except that aluminum lithium alloys have major fatigue issues, it turns out. And so they never totally made it in the aerospace industry, except they still make components of it. I think that actually the seat frame is aluminum lithium, because, you know, if your seat cracks while you're in the plane, I mean, it's not the worst, right? Okay. So let me give you another, let me stop sharing because I'll do this on the board. There's another interesting application which has historic roots. So the fact that melting temperatures tend to go down when you add stuff to them. And the technique is called transient liquid phase bonding. Or TLP. The idea is as follows. So let's say I have the classic sort of pseudo eutectic phase diagram. I mean, I could make it a full eutectic, but really all I need is the melting points to go down. That if I take a piece of A and I put a small amount of B on it, I could sort of electroplate that or find some, or do some other thin film deposition method. And I put it between another large piece of A. So you're going to use the B to bond A. So what happens when you hold this at a temperature here? So this is a temperature where both the A and the B are liquid. But what's going to happen if you think about interdiffusion? So these things are going to start interdiffusing here, right? So the B is going to get diluted by A. And remember, it's only a small amount of B, right? So A will obviously get some B in it. That's a much smaller effect. So what happens when the composition of B gets richer in A? Right? At some point it melts. It melts simply by holding things at some temperature without any temperature change. So at some point, this zone of B melts here. And it actually, in reality, does it very fast. Now, what happens if I just wait more? By the way, usually this zone, this film is like very small, like 20 micron, 50 micron, sometimes 100 micron. So even when it melts, it's held in place by capillary forces. It's not like it runs out. So what happens if I keep on going? Because the amount of B is small, the B will just start to diffuse away, right? So my composition keeps on drifting. And since the amount of B is very small compared to the A, at some point I'm solid again. So even though you are isothermal here, you go solid, liquid, solid. And why is this useful? It's because you can use this as a technique to bond materials. You can use B through its melting point lowering effects as a way to bond pieces of A together through a melting solidification transition, but without ever changing the temperature of the piece of material. So this is very different from welding, right? So if you weld metal, you have to kind of like, put a torch on it or an arc. You have to locally heat up the material. And then when you solidify it, and as it cools down, you get all kinds of thermal stresses because the joint was at very high temperature, but the body of the material was not. And that's why welds sometimes have issues with fatigue cracking, because they have thermal stresses built in them. Here, you can take a whole piece, bring it to temperature, bond it, and then slowly bring it back down and keep the piece at homogeneous temperature. So this is actually often used, well, maybe often is an overstatement, to bond titanium. And the reason is titanium is extremely hard to weld. One other problem with titanium, because titanium is extremely susceptible to hydrogen and oxygen incorporation. So any environment where you have hydrogen or oxygen, the titanium will soak it up and embrittle it, and so that makes welding of titanium particularly hard. And the way you can see that the way it's actually done, so if A is titanium, then people use often like electroplated nickel to bond the titanium. And you can see that from the phase diagram. Go back to sharing. Sharing is caring. Okay, if you look at the titanium nickel phase diagram, what you see is that there's some region, right, where you can hit only the solids, and the liquid. And if you anneal in that region, so you don't have to go to the melting point of titanium at all to bond the material, and you can stay below the melting point of nickel, and you can bond the material. One of the reasons, you could in principle go lower, right? In principle, you could say, I'm going to do TLP here. I'm going to just hold the thing here. What happens though here is that you tend to make intermetallics, and they tend to embrittle the alloy. In principle, they should diffuse out, but you just have to wait a longer time. So people like to do TLP above the temperature of all the compounds. TLP was historically known already, and historically I mean in quite a long time ago in history. Not that they called it TLP, but it was used to bond, do delicate artwork on gold. This is from Tutankhamun's dagger from his tomb. And if you sort of look at I have one with the scale somewhere. Well, this says, enlarged times 10, but of course I've already like cropped that picture and everything. But if I remember, these little spheres here are of the order of they're less than 1 millimeter, I thought. This is actually this piece. I think is not much larger than it's sort of like a big ring, but really big ring. But what you see is the artwork is extremely fine, and the way they did that is by having a base piece of artwork, and then they laid out gold beads or gold strips on it. And the way they do it, the way they would bond it all together, we sort of figured out from a Greek text, which is not in Greek here, but was translated in the Middle Ages. And you know, I'll read you just a few pieces of it here, but some of the cool stuff will show up towards the end. You know, it's sort of be ready at hand when the charcoal is beginning to glow, blah, blah, blah. And then you use the bellows, of course, whatever, to make it hotter. Okay, watching with care, you will see the outer skin of the gold begin to glow. Blah, blah, blah. Okay, and here we go. You will then be beautifully soldered without any need of special solder being applied to it. And this might be called the first firing. And then he says, the first soldering ought not to be called soldering at all, because soldering is melting a joint, right? But rather firing in one piece. And this is sort of one of the keys, right? They fire the whole thing in one piece. And then comes the chemistry, because there is so much virtue in the verdigris, which is a Greek word, and then when combined with the salts of ammonia and borax, that it only moves the outer skin of the gold and so amalgamates it all together. So it only moves the outer skin of the gold, so that you don't melt the whole thing, and you use verdigris. What do you think verdigris is? Verdi is
copper.
Yeah, verdigris, because the verde, right, in Latin, and maybe in Greek too, and still in Italian, is green. And what is green? Copper oxide, right? If you ever seen like statues, like if you go to Europe and you see bronze statues that have sat around forever, they basically look green, right? Because the copper that's in the brass has oxidized. So they used copper to do the bonding. I gave you the Oxford Dictionary here of verdigris if you want to look at it. You can see that works by sort of working somewhere in this temperature regime. So if you take gold, like a big piece of gold, and then you want to put like, say, small beads on it, all you had to do is to a little bit of copper paste, which was the verdigris, right? So it was actually copper oxide, but remember that the high temperature will reduce the copper oxide to copper, and you could amalgamate all things together. And so this was done already in the Etruscan time. There's a really cool book, which is getting a bit old now, but there was a professor who worked in the 50s and 60s at MIT, Cyril Stanley Smith, who wrote a book, The Search for Structure, which is a very cool book if you're interested in archaeology and material science. He applies like real material science principles to archaeology, because he was actually a professor in material science. So it's quite a good read. There's some other really nice examples in there. Okay. Let's go back to the board. So a lot of this is sort of using some quantitative knowledge we have about transport and kinetics and integrating that with our knowledge of phase diagrams. And I want to give you more examples of this. I want to show you that you can understand a lot of non-equilibrium behavior from phase diagrams. So understand phase diagrams under non-equilibrium conditions. And I'm going to do two cases. Lack of diffusion in one of the phases, which is usually the low temperature one. and not in the other when you have a two-phase equilibrium, and then lack of nucleation. So to give an example of lack of diffusion, I want to go back to the importance of diffusion in the solid to describe what happens during solidification. But I like to use solidification because it's easy to talk about a liquid. Otherwise, I have to talk about two phases. But this would be an issue whenever you have two phases in equilibrium with different kinetics for diffusion. So let's say we have sort of just the beginning of a two-phase region here. So here we are liquid, and here we are sort of our alpha solid, right? So this is solid. Let's go through what should happen in true equilibrium when I solidify. So if I have a impurity content like this, so as I solidify it, the first solid that form would have this composition. Let me call that X1. So let's say I have a liquid pool and I start to form a solid with composition X1. Okay, so now I cool further. I'm going to do this in discrete steps because it's easier to explain, but in reality, this would be a sort of slow, continuous process, right? So let's say now I cool further down to here. What happens now? So the equilibrium solid concentration is X2. So what has to happen is that, so I have more solid, right? You can figure that out from the lever rule. So this is X2, but this has to become X2 as well, right? Because the composition of the solid has to be homogeneous. So what has to happen, the process here that has to happen, because I started out with X1, and then I form a shell of X2 on it, but to fully equilibrate that, the X1 has to be enriched in B. So B has to diffuse through this solid, or A has to diffuse out, right? Because X1 is less than X2. So to fully equilibrate the solid, you have to have diffusion in that solid, and that's usually orders of magnitude slower than the liquid. Right? Diffusion in solids can easily be 4 or 5 orders of magnitude slower than diffusion in the liquid, even when at the same temperature. So usually that doesn't happen. So what will happen most of the time is that whatever I formed stays there and doesn't update its concentration. So I have X1, I have X2, and then, you know, if I go to another temperature, I have X3. And so you get what is called a cored solid, or coring is the term, because the core of the solid is different than the shell. And again, you know, in reality, you wouldn't do this by stopping at different temperatures, right? You would go continuously down, and so this composition difference would actually be a composition gradient. So what is the actual composition of the solid then? So normally, if I'm at the green temperature here, I would have to have composition X2. But if I'm cored, then my composition is somewhere between X1 and X2, my overall composition. So my composition is somewhere here. And if I'm at the orange temperature, again, my composition is some kind of average of X1, X2, and X3. And so maybe my composition is here. So there is a non-equilibrium solidus, which I'm going to draw in dashed lines here. which tracks the real composition of the solid. So this is the maybe I should call it not real, but non-equilibrium composition of the solid. Okay, so that may seem like a mystery to you, but do you see that you can actually calculate what that solidus is? If I gave you an equation for the equilibrium solidus, and I gave you an equilibrium for the liquidus, you could calculate what this non-equilibrium solidus is. You could calculate the extreme of it, right? The one where you assume. Do you see? I'm not asking you to do it now. Maybe some other day I'll ask you to do it. But you see that that is possible because I would know at every temperature the composition of the solid that precipitates out, and from the lever rule I would know how much precipitates out, right? So I have all the information, right? So there's a few consequences to this. One is where is the material, at what temperature is the material completely solidified? Because in equilibrium, that's here, right? So in equilibrium, this is the temperature. I'm sorry, there's a lot of stuff starting to appear here. This is what I'll call T equilibrium, end of solidification. Right? Because that's when in the equilibrium diagram, I cross into the solid. Where is the non-equilibrium end of solidification? Think about that. This is one of these questions that is actually much simpler than you think. Where would the non-equilibrium end of solidification be? Anyone wants to make a guess?
Is it where the non-equilibrium composition line reaches the vertical?
Yep, it's right here. Exactly. Exactly right. And the way you can know this is because when all is said and done, the overall composition of your solid has to be the same as what you started with, right? It's not like matter disappears here. So if this is the average concentration of the solid, well, this is where you hit the overall. So this is where solidification is done. So first of all, you have a lower. So this now is the T non-equilibrium end of solidification. And so what this thinking allows you to do is to figure out the range in which you may have to operate for any phase transition, right? Because if everything is perfectly in equilibrium, you have great diffusion, you're going to be done here. If you have no diffusion in the solid, you're going to be done here. If you're slow and you have a little bit diffusion in the solid, then maybe this non-equilibrium solid will track up a little and maybe you're done somewhere in between. Okay. Now here's the bad thing. Let's say I solidify this material in non-equilibrium conditions, right? And then I heat it up again. Where does it start melting? It starts melting much earlier than I thought, right? Because how did I end up here? Because at the end of solidification, I made some solid with this composition, right? Because my solid isn't updating as well as it should, my composition is drifting way over to more B, right? In equilibrium, I should have never gotten further than here, right? The liquid should have never gotten further than this, and the solid should have never gotten further than this. In non-equilibrium, my liquid made it out all the way to here. My solid made it all the way to here. The outer core, I'll call that X4, right? My outer core is X4. So if I start heating this thing up, I start melting already at this temperature, which can be much, much lower than the temperature that I thought I had. So non-equilibrium distribution of elements can really trick you, right? Because so this is a case where the melting point of your material would be much lower than you think it is. But other bad things could go on, right? Like, what if this phase diagram out here became a lot more complicated? I don't know, maybe there's a eutectic out here, or there are compounds forming. Then I'm forming compounds that I didn't know I was going to, right? Because the composition of my liquid is drifting out much, much further, because in some sense, my solid isn't taking up enough B. So you should be aware of complications with non-equilibrium phase transitions. But there's also a power here that you can actually, if you wanted to, you could mathematically calculate where all these points are. All you need is an equation for this curve, an equation for this curve. And these guys are often linearized if you want to keep it really simple. That makes your life really simple. So this is obviously, again, a big problem in industry. You know, in industry, nobody has time to do any phase transitions in equilibrium. Definitely not solidification. If you do solidification again, right, don't think of like a little sample you may take in the lab. When people solidify in industry, it's like cubic meters at a time, right? So there is no way you're going to do this in equilibrium. And that shows up if you actually look at a real microstructure and you etch it. Again, this is, I'm going to show you my favorite aluminum copper alloy again. This is an etched microstructure of aluminum copper. And what it actually, the dark spots are richer in copper. And this is actually a solidification microstructure. You can sort of see it from this kind of dendritic way. It's sort of the way you solidify is in a sort of dendritic way, and that has to do with because of the heat transport and the solidification. And so these holes here get solidified last, and what you see is they are enriched. Oops, they are enriched in copper. So you have this enormous disparity or dispersion of your of where your elements are. And again, you know, the way that this is dealt with, the way industry deals with is, again, it's not by annealing the crap out of things, which is, you know, in industry, everything is about throughput and low energy cost. So you don't just put this in some furnace for like 15 days and anneal it, you just hot roll it. So it's, again, mechanical kneading is a much more effective way to homogenize materials than annealing. And this is classic. This is done in the polymer industry. Like, you know, mechanically mixing things, even when they are solid, is a much more effective way to mix things than annealing, because, you know, diffusion is just in general a kind of slow and not very efficient process. Okay. As good engineers, though, you can use this seriously to your example in a technique called zone refining. And I apologize that I know some of you have seen this already, what zone refining is. So you can pass out now for a second. Well, a minute or two, if you want to. But zone refining uses this non-equilibrium aspect of phase diagrams to actually purify materials. And the basic principle is that you can, if you melt something, you can precipitate out a solid that has lower impurity content. So if this is the general impurity axis, right, that the solid in equilibrium with a liquid has a lower impurity content. So in principle, if you think as an engineer, there should be something you can do to use that to refine materials, right? Because if I every time make a liquid, if I could, this is to say the liquid with my impurities, I precipitate out some solid, I'm going to get this concentration. And let's say I separate that material now and I throw away the rest of the liquid, then I heat that up, right? And now I precipitate that out, I get even less impurity. So you can see that kind of repeated solidification and melting could in principle lead to purifying something. And that's what's done in zone refining. And in zone refining is done a little more intelligently. Again, you rely on this phase diagram that looks like this. Yep.
Can I share a screen?
Oh yeah, sorry.
Thanks.
You should tell me much sooner, man. People have missed all my brilliant explanations. Okay. So zone refining, again, relies on the same type of melting point lowering phase diagram. And what's actually done is that if you take a bar of material, and of course, this is the classic approach to purify silicon. So this could be a Czochralski grown silicon bar. What you move across it, you use an induction coil. So you have a coil that goes around it, which locally heats the material. So you start by very locally melting things. And if you make the melting zone small, then capillary forces can keep it in place. So you don't have to worry about the liquid running away. Okay, so let's say you have a silicon or any material with some impurity, right? And this is your impurity content. So let me call that X0. So then you move that zone to the right. So basically you either slide the bar, but actually more often you slide the induction coil. So your liquid zone moves. So you've made solid here. And that solid will have a lower composition, a lower B composition, right? So that solid will have composition, what do I call it here? X1. So I'm going to draw the composition profile. Basically what I'm going to do is I'm going to move this zone all across the bar, and I'm going to draw the composition profile as a function of this direction. Since I call composition X, maybe I should call this Y, okay? So this is Y. So if this is X0, then the first solid I make has a much lower composition, X1. But I've paid a price for this, right? Because I precipitated out less B in the first solid, my liquid is enriched. Right? Because mass doesn't get lost, right? It went somewhere. It stayed in the liquid. And the liquid moved to the right. So my liquid has moved up in composition. So the next time I move this zone, I still get some gain, I still get some purification, but it's less. Right? So now when I move the zone again, you know, maybe I'll have X2. So this is Y, right? I move the zone. Sorry, so I have a point here, Y. And at some point, nothing's going to happen when I move the zone because my liquid gets more and more enriched. And at some point, it reaches this steady state condition here, where the liquid reaches, I'll call it LXL or something, right? And now it precipitates out the same concentration of solid that it takes in on the other side. So at that point, it's in steady state. So when I draw the composition profile as this thing moves through the bar, it's going to look something like this. And of course, at the end, right, I'm not taking out anything new. So there, the concentration has to go up, right? So this should be the same length of the bar, because the average of this curve has to be x0, because I'm not removing anything from the bar. I'm just moving it around, right? The impurity is conserved. So you could say, well, that was fun, but I only got a tiny piece of material with lower concentration. So what does the really smart engineer do? This was the Kansas City engineer. No, sorry, just that's very bad of me. Okay. What does the really smart engineer do? You do it again, right? You move the zone again back and forth. So you start all over again, and now this becomes your input in the beginning. So now this curve goes like, right? And you do it again and again and again, and after a while, right, this curve will stay very low here and go up and then go way up, right? So every time I move this zone across, basically I'm dragging impurities to one side. You see that construction? And so what do I do in the end? Well, in the end, I just chop off the bad piece, right? I decide what my critical level of impurities is that I want to tolerate, and I chop off that piece of silicon. And do I throw it away? No, right? I use some other purification technique on it. The beauty of this is that you can get almost infinitely pure. If I do this many times and I do it fast enough, why do I have to do it fast enough? Well, what happens if I don't do it fast? Well, I have a solid with non-homogeneous composition. If I let it sit there forever, it's just going to homogenize again, right? In the solid state. So I can't like do this for days and days and days, because I will get solid state diffusion that will make stuff diffuse from right to left here. Anyway, so I keep on doing this enough and I can get amazingly pure silicon, right? So zone refining is the key to high purity silicon for electronics, right? So there are three magic things to silicon, right? The chloride process, which does the first purification. So silicon oxide is turned into silicon chloride, which is then refined. Then you do Czochralski growth to make nice single crystals. And then you can do zone refining. You can also do it in the other order, right? You can first do zone refining and then do Czochralski growth, which is the way it's actually done. So you can make this infinitely pure, right? And you know what? It's all about because of melting point lowering. You see why this is so important? You know, if you forget everything about this class, right, you should remember melting point lowering, because it is such a crucial thing in industry, right? It's used for everything. Actually, you know, when I meet people that have taken my class 20 years ago when I was still at MIT, you know what they remember of this class? Well, it's what they say they remember. The bicycle tire experiment is what they remember. But I think that they actually remember melting point lowering as well. They just don't think it's as cool as the bicycle tire experiment. Okay, zone refining, super important. And again, if you look into some thermodynamics textbooks or some electronics textbooks, this is actually discussed in some textbooks on electronic materials because it's such an important process. They'll actually show you equations for this, right? Because, you know, if you're a math whiz and you like to have some fun, you can do this, right? If you take a line, an equation for this, an equation for that, and usually people just take them as linear, you can actually calculate what this profile is that comes out, which is kind of fun. Well, you know, some people's version of fun, okay? Okay, so that was some examples of both bad things and good things when diffusion does not happen, okay? So the next thing I want to do is what happens when nucleation doesn't happen, nucleation that's required for new compound formation. So let's do this with a diagram which has just one compound in it, so that we can do this in a sort of reasonable way. Okay, so let me draw a diagram with a compound. And it's going to be a good diagram. It's going to be a large diagram. Sorry, that time's over. Sorry. Okay. Here's gamma. That's my compound. It's a beautiful compound. We're going to make it go away by some eutectics. Does it look like I enjoy this drawing phase diagram? It does, right? Okay. And you can fill in the two-phase regions, right? Okay, so, you know, A is basically an elemental solid with some B in it, and beta is some elemental solid with some A in it, right? And usually those are not particularly hard to nucleate. So when you like solidify here, you know, usually making like FCC or BCC or whatever isn't that hard. But let's say we're in a situation where the intermetallic, this compound is like fairly complicated crystal structure. Maybe it looks very different than the local structure in the melt, so it's hard to nucleate. And what that means is if you learn, you know, you've learned nucleation theory as an undergraduate, but sometimes it's hard to nucleate because if the local configurations in the liquid don't look anything like the ones that in the solid that has to form, then the fluctuations that are required to get you to the solid are very infrequent and very improbable. And then sometimes the nucleation time is really long. Okay, so we're going to work under that scenario. So you cool fast enough to not nucleate. So the question is, if gamma cannot nucleate, what happens to this phase diagram? So, you know, if you're a student from a lesser place, like a graduate student from, I don't know, MIT or, no, just kidding, then you would say, you know, no, phase diagrams are equilibrium. You know, you can't learn anything about non-equilibrium. And that is such BS, right? That is people who've never had a good thermal course. Because you can learn an awful lot of non-equilibrium behavior by understanding where the phase diagrams come from. So again, these phase diagrams come from a competition between free energy curves, right? And so if I tell you gamma cannot nucleate, all I'm doing is removing the gamma free energy curve. I'm basically saying gamma is not an option. So let's look, for example, how would this phase diagram look like if I was at this temperature, but I had no gamma? Okay, let's draw free energy curves. This is a good refresher. So the equilibrium behavior, right, is alpha, beta, gamma, some common tangents. Beta, gamma, and then here you have alpha plus gamma, gamma plus beta, right? By now, this is like child's play for you, right? Okay, and let's do some magic. I need to put in the liquid. So in equilibrium, the liquid wouldn't do anything interesting, right? Because it would be above this common tangents. Right? And that's consistent with the phase diagram that the liquid doesn't appear anywhere. So what happens when gamma is not there? Well, then I just have an equilibrium with the other phases that are there, right? Which is alpha, liquid, and beta. So what's that going to look like? I need more colors. So I just removed the gamma free energy curve, right? So goodbye, gamma's gone. So what's my new equilibrium? It's between alpha and the liquid and beta and the liquid, right? In this case. So I have, okay, I'm a bit messy here. This comes a little in here. So I have alpha, alpha plus liquid, liquid, and liquid plus beta. I know it looks messy, but take a. Okay, so what am I really saying? What I'm saying is that if gamma gets removed, so let's see what would happen to the phase diagram. So here I have, let's look at the two-phase union. Here I have liquid plus alpha. Will anything change to that when gamma gets removed? No, because gamma is not involved in this two-phase equilibrium. So these lines will stay exactly where they are. But then the eutectic shows up, and that's where gamma normally would come in. And except now I say, well, gamma can't appear. So that means that basically the liquid and alpha just kind of continue on their happily marching two-phase region, right? Same on this end. I'm going to remove this line now. The magic of digital technology. Okay, so how's this going to end? In a bad way? No. How's this going to, what's this going to become? You know, this is like a phase diagram is like a Da Vinci painting. You know how they would often find that when they did X-ray of the canvas, there was something else below it because people recycled their canvases at the time. And sometimes a totally different painting below the painting he actually made. So in a phase diagram, there's always a hidden canvas too. So what does this become? If gamma's gone, it's a eutectic, right? Because I just have two phases and a liquid coming through. So this becomes a eutectic. I mean, it's beautiful, right? Now, before you think this is esoteric, this is actually remarkably useful. So I have so much to say that I'm thinking about what order I have to say about it. Okay. A reason this is very useful. Well, it'd be useful to explain non-equilibrium behavior, but people who try to make amorphous metals, like metallic glasses, right? They look for things where they can, you know, bring the liquid down to really low temperature so that its kinetics is bad, so they can essentially solidify it as an amorphous state, right? So you can't do that if the lowest point where the liquid appears is really high temperature, because then you simply cannot quench fast enough. And the other thing is that the first amorphous metals that were made required enormously fast cooling rates, like 1,000 degrees per second. So they were done on like a spinning wheel, and you splash the metal on it, you make ribbons. Now there are amorphous metals that can be made with cooling rates of just a few degrees per second, which means you can start doing it at an industrial scale, right? There's no way you can take a large pool of metal and cool it at 1,000 degrees per second rate, right? But if you down to like a few degrees per second, then you can start making large volumes of that. And hey, what are amorphous metals good for? It was such a hype in the 90s and the 2000s. You know, there was a famous Stanford professor who was on infomercials with this, like, you know, where they put your little, like little picture in the corner of the TV screen, and was endorsed by a Caltech professor. What's an amorphous metal good for? Think about it, right? No crystalline structure, no grain boundaries, none of that. What do you think that does well for you? You should think like engineers, right? Let's say you were in the 90s, right? And amorphous metals were new. This is how you invent new stuff, right? You have to kind of understand what it gives you. No grain boundaries, no crystal structure. What? That does a lot of bad things for you, but what are the good things it does for you?
You said infomercial, so I think cooking, but I don't know if that makes sense.
No, actually the first infomercial was for golf clubs. And that should give you a sense of why it was so good. The first sort of population of metallic glasses was golf clubs. And actually they were so good that in the PGA Tour for the longest thing they were forbidden. And I don't know if that's still true. I think that may not be true anymore because they were seen as an unfair advantage for some. Why? What would you want? What do you want from the head of a golf club?
High elastic response.
High elastic. Did you say elastic?
Yeah.
Yeah, perfect. You want perfect elastic response. You want high elasticity, so you want a lot of elastic range, right? So you can kind of like when you hit the ball, you can make longer contact with it and then release that energy. And you want no dissipation. You don't want no dissipation of the thermal shock, not the thermal, the mechanical shock when you impact the ball. And that's why you don't want grain boundaries, right? Grain boundaries have caused dissipation of mechanical energy. So the first super elastic applications of metallic glasses were in golf clubs. Caltech invented. You see, you know, Caltech does important things for the world. Just kidding. Okay, more importantly, other things that grain boundaries are bad for, hysteresis, if you do magnetic switching. So transformers, I'm going to come back to this phase diagram, I promise you. But what does a transformer do? Right? I'm not very good at this stuff, but so if it's slightly wrong, my apologies, right? But you have a magnetic hysteresis loop, right? None of us is good in magnetism, right? Well, anyway, I'm sure some of you are. And one is like applied field, and the other one is the magnetization or induction, whatever, right? So you know that every time you go through this loop, you waste energy, right? Because that's the dissipated energy in the loop, right? And sadly for us, if you're running at 50 hertz or 60 hertz, right, depending what part of the world you're in, this is kind of important because you're doing this 50, 60 times a second. So the electrical energy wasted in transformers in the world is as much as the electricity consumption of all of Australia. That's just transformers, right? We haven't done anything yet. So on average, electricity is transformed about 6 times before you actually use it. I feel like we need a cocktail party. This would be much better to tell you these things at a cocktail party. So what causes this? What causes this is the pinning of domains, right? What you do in a magnetic material is that you switch the domains, right? You switch the polarization. And if that polarization switching is not perfect, right? If it gets pinned by things, then you, what was I going to say? Then you have hysteresis, right? Okay. So what causes pinning of domains? Well, what causes pinning of domains is things like impurities, things like grain boundaries. So if you can make this without grain boundaries, then you actually have no switching of no hysteresis, right? Okay. So you make a material with no grain boundaries. And how do you make a material with no grain boundaries? You make it amorphous. So this is not done yet, but people are still looking really hard for an amorphous metal that is based on iron. Because if it's based on iron, you can do magnetism with it. So if you can make sort of a high iron content amorphous metal, you would actually be able to reduce significantly hysteresis losses. So today, the way hysteresis losses are minimized is more by a macroscopic construction, right? You do things like you make small transformer cores are made out of soft magnetic materials, and you stack small plates together so that you have sort of less motion of the magnetic domains that you need. So, okay. Okay, back to this. So the way people do this is that they look for complex phase diagrams with these buried eutectics. So they look for phase diagrams with these non-equilibrium buried eutectics. So because the lower this metastable eutectic is, the lower you can bring the liquid if you rapidly cool. So if you rapidly cool, you can often prevent nucleation of the compounds, especially if they're complex. So you tend to look for phase diagrams in which the compounds are complex, like they have complex crystal structures that are difficult to nucleate, and where the sort of extrapolation of the liquid and the elements, those two phase regions, lead to a very deep eutectic. Because once you hit a few hundred degrees here, you know, the kinetics of crystallization is really bad, and you can just literally quench the liquid down all the way until it's an amorphous solid. And so there's a lot of work going on in making, and this is done in like high component alloys, ternaries, quaternaries, sometimes quintenaries, to find these deep hidden eutectics. So. Okay, one other thing I have to say about this. So the solubility limit in non-equilibrium, so this line here, the solubility limit of B in this phase in non-equilibrium is higher than the solubility limit in equilibrium. And this is always true. And you can sort of rationalize that from the free energy construction, right? Because I know it's getting a little messy here. Let me just redraw this. So if you look at a solubility limit, so let's say that's my alpha phase, and normally I have an equilibrium state with gamma. So I have a tangent here. If I go to non-equilibrium, then by definition my competing equilibrium is higher in energy. So maybe if gamma doesn't happen, I'm in equilibrium with beta, and that means that the tangent always sits higher, right? The chemical potentials in the non-equilibrium, equilibrium, which is a mouthful, are higher. So you see that this point here is at higher solubility. And that's why in non-equilibrium, the solubility limits are always larger than in equilibrium. And this is a general truth. And this is actually also used, this is used, for example, to get higher doping levels in materials past the equilibrium limit. So if you can form your material while it's in equilibrium with a non-equilibrium counterpart, right? Then you can actually infuse more doping into the solid. And then if you bring it down in temperature, hopefully you can retain that. So you try to form your solid or nucleate it in equilibrium with a non-equilibrium condition. I think you all get what I mean, right? So this is done to dope thermoelectrics, to higher, sometimes to dope semiconductors to higher solubility limit. But it's sort of a fairly classic approach that's not often explicitly spelled out. But if you analyze synthesis process of some materials that have to be highly doped, they often involve this kind of non-equilibrium equilibrium. Okay. So the last sort of non-equilibrium case that I want to discuss, we still have time. Yeah, is spinodal decomposition. And the best way to explain it is when you have a non-convex free energy. So if you have a free energy surface like this, and as you know, the equilibrium in here is defined by a common tangent. But there are two different regimes in this two-phase region, two different kinetic regimes. The first one is, let's say I quench a composition in here. So it's in the two-phase region. I'll call this one. It's in the two-phase, but it's in the convex part. So in equilibrium, that should form two phases, but as you'll see, that it has a hard time doing it. And the reason is that when it makes small fluctuations, when you're in the convex part, when you do a small fluctuation, you know, the chord, if you do a small fluctuation in something that's a bit richer in A and a bit richer in B, the chord is above the curve. So in this area, small fluctuations have positive energy. And what that means is they require a large enough fluctuation to actually set in nucleation and growth. If you do this in region, what I'll call region 2, which is the concave part, if you do this here, so 2 is the concave part, there any small fluctuation lowers the free energy because the chord is below the free energy curve. So in the concave part, any small fluctuation causes a delta G that's negative. So what you'll see is that the transformation kinetics will be very different, right? So in this regime, in the concave regime, the material will instantly start phase separating because there's no, even the smallest fluctuation can't stop it. As soon as it sees any small fluctuation of composition, it will start to decompose. If you're in the convex part, you need a fluctuation of a certain critical amount before it can form the second phase, and that's what's called nucleation growth. So these two regimes are, of course, separated by the point where the second derivative is 0, and those points are called the spinodal. So, and if you plot them on the equilibrium phase diagram, so let's say this is a solid solution. This is the two-phase region. There's a locus of points in there, and this is called the spinodal. So it's spinodal, not spinodal. So if you quench in here, you have no metastability. Basically, the solid solution is completely unstable with respect to any fluctuations. If you quench in here, you require nucleation and growth, so you might be able to maintain for a while a stable solid solution. So this kind of instability is most common in composition. But in general, it sort of happens whenever some derivative, the square g with respect to any parameter, when this turns negative, right, you tend to have instability, not even metastability. Remember that I talked to you about, you know, if you make, for example, if you make this length, right? I told you about sort of inhomogeneity of plastic deformation or even elastic deformation in principle. So all of these instabilities. The one that's actually quite common is instability with respect to an order parameter, negative. So we didn't talk much about the formalism of ordering, but in I think it's in chapter 5 of Gordon, they talk a little bit about ordering. So if you quench a solid solution into a domain where it should order into a compound, you can sometimes keep the disordered state stable, but not if the second derivative with respect to the order parameter is also negative. In that case, you get sort of spontaneous instability. So. Okay. I think I'll stop there for today. Any questions about this? A few minutes left.
What's the symbol for the order parameter?
I used an eta. So normally it's a common symbol used for order parameter eta.
Okay, thanks.
You're welcome.